Good morning, students. Today we are going to discuss about radial basis function network. So what exactly the radial basis function network is and why we need actually the radial basis function network, we'll discuss. Okay. So as you know that we have a data available with us and we'll give this data to the model. So data could be of two types. A data could be of linearly separable or it could not be a linearly separable. There is a possibility whatever data is coming to me, maybe the data is linearly separable or maybe the data is not linearly separable. So what you will understand with linearly separable, as we discussed earlier, when we say the data is linearly separable means if I'll draw a line, okay, I have a data. So you can see here this red point and the blue point are representing the data. And I want to segregate these two data or separate these two data into two different classes. So if I'm able to draw a straight line and I'm able to separate this data into two parts, then we can say that data is linearly separable. So this is called a linear boundary. And with that straight line, if I'm able to separate the data into two parts, then we can say this data is linearly separable. So when your data is linearly separable, then things will be easy for us. We can divide the data into two classes very easily using multi-layer perceptron also. Okay. Now, when my data is not linearly separable, when I have a data which is not linearly separable, then what we have to do? So first of all, you should know what is not linearly separable. So you can see here again I have a data which is represented by red dots and blue squares, and I want to separate these two data. So is it possible to separate these two data using a straight line? No, I cannot separate. If I separate this, you can see here you have still here this red data. Okay, so I cannot separate this data into two different classes. Same way, suppose I have a data in this way. So can I separate this data through a straight line? No, it is not possible. Again, so this is called non-linearly separable data. So whenever you have a non-linearly separable data, that time your radial basis function will come into picture. So radial basis function is used whenever your data is not linearly separable, then you can apply this particular network and you can classify your data into two different classes. Okay, so it's artificial neural network that use non-linear radial basis function as activation function. So why we have taken this as a this name, because we studied earlier that we have various activation function. So this particular model is going to use radial basis function as an activation function. So they have given name as radial basis function network. Okay, and what is the use of this particular network? It is used to separate your data. If your data is not linearly separable, then you can apply radial basis function, and in radial basis function you are applying the activation function, which is RBF again, and you will separate your data into two different classes. So where exactly I can use this particular network? So if your data, if you have a data which is continuously changing, or we can say time series data, when you are having time series data, suppose you want to do the stock prediction, or you want to do the prediction of the temperature after every minute. So this data is changing every time. So whenever you are having such kind of problem statements, that time you can apply radial basis function network for classifying your data. So this is your basic of radial basis function network, neural network. Okay. So what we can say, it's a multi-layer perceptron, as we discussed about the multi-layer perceptron. So the multi-layer perceptron, it's type of multi-layer perceptrons which is having one input layer and one output layer, but strictly we will have only one hidden layer into it. Behavior is same like multi-layer perceptron, but the strictly it is following only one hidden layer is available into it. So that is the difference between a normal multi-layer perceptron and radial basis function network, that it consists only one hidden layer. Okay, so what we are doing here, as you know that what we are doing in every multi-layer perceptron or perceptron, what we are having, will be having input data which is representing by x. That input will be multiplied with weight. Okay, and then you will apply bias into it and you will get your value, which is, suppose I'm representing through z. Now you are getting this result. You are getting this result from every multi-layer perceptron network. Now you will apply an activation function on top of it. So when you are applying radial basis activation function on it, then we'll say it is a radial basis neural network. Okay. So the special radial basis function will be applied on this type of problem statement, and you will get your final outcome. So what it will do, see, you are having the data available with us. So what it will do, it will convert whatever input parameters will be available, convert those input parameters into the high dimension space so that we can feed the data into the network which is linearly separable now. Right? So what I'm going to do here, at the hidden layer, we use a non-radial function basis function as an activation function, which is going to convert the input parameter into the high dimension space. So your RBF function will convert your input data into high dimension space, and then which is feeding into the network to linearly separate your problem. Okay, so this is the architecture of your RBF network. So I hope it is clear to you. Okay, just take a simple example that how where exactly the radial basis function network will work. See here, you have data available in this way. Your data is available in this way. Now, is this data is linearly separable or not linearly separable? You can see here two classes we are having. One is represented by star, and another is represented by circle. Can I draw a single straight line here in any way? Okay, can I draw a single straight line anyway in this way or in this way? Any straight line which will separate my data in any way? No, it is not possible. It is not possible. I cannot segregate my data with a single straight line. So what I have to do whenever my data is not separable linearly, I have to apply non-linear radial function. Okay, so when I apply non-linear linear function, what are the different way of applying the non-radial linear function? What I can do, I can increase the dimensionality of my data. So what I can do here, I can increase the dimension. Suppose if my data is 2D data, I can make it into 3D, and I can try to separate my data into two different classes. Okay, this is one way of converting your non-separable data into separable data. The another way is I can expand the direction either horizontally and vertically. So expand the direction horizontally, and we will compress the direction vertically. So what I'm going to do, whatever data is available, I'll expand it. So if you'll expand your hand in this way, and you'll compress in other way, compress in vertically and expand the horizontally, there is a possibility that your data will be separable. So if you remember, my data looks like this. So what I am applying here, I am applying expanding in horizontally and compressing vertically. So if I'll expand horizontally and compress vertically, what will happen? You can see there your data will look like something like this. If your data will look like this, the resultant data will be like this. So can I separate my data linearly? Yes, I can separate my data linearly, because with a straight line I can separate star and the circle in two different classes. So in this way your linear RBF network will work. So what I'm going to do, randomly we are going to select a center of your data. So this is a random selection of your center, and then we are going to draw a concentric circle around the centroid of my data. Fine. And now whenever I'm applying the expand or compress on my data, I can apply any of the function. I can use these three functions. One is called multi-quadic function, which I can apply, where the formula is theta r of r equal to r square plus c square of power of 1 by 2. And here c is nothing but your constant, which should be greater than 0, and r is the radius. Fine. The same way I can apply inverse multi-quadratic. So my inverse multi-quadratic formula is this 1 divided by r square plus c square the power of 1 by 2. The same way I can apply another function which is called Gaussian function, and which is having the formula exponential of minus r square divided by 2 sigma square. So I can apply any one function to expand or compress my data. Fine. So these are the functions which are available with me. Now, as we discussed earlier, how the architecture looks like. We have an input layer available with us. So these are my input layers. So inputs are given by x1, x2, and xn. So and there will be there is only one hidden layer, which is representing here to h1 to hm, and you are multiplying x1 with the weights. So weights are assigned at every layer, and finally you are getting the output, which is represented by f of x. You have input layer, hidden layer, as well as the output layer. So this is your architecture. Fine. So what we can say, this is a two-layer feed-forward neural network, and hidden nodes implement a set of radial functions. So at the hidden layer, what I'm using, I'm applying radial basis function as an activation function, or you can apply Gaussian function as an activation function. And what will be the output? Output node implement linear summation function as multi-layer perceptron. So at output layer, we'll get the same linearly separable result as we are getting in MLP. And training and learning will be always fast here, and network is very good at interpolation. So these are some of the tasks which are having related to radial basis function. Now, if I want to compare the radial basis function with multi-layer perceptron, what I can say, it is a local receptive field, or we can say we will take the input which is near to the receptive field. I'll not consider all the input for getting the final output. Just I'm considering the input which is near to receptive field. Okay, but in this case, we are going to draw a hyperplane. I'm going to draw a global hyperplane. So when I'm saying global hyperplane, so all inputs are taken into consideration. Okay, and this is the first difference. The second difference is here we have a large number of hidden neurons. So number of hidden neurons will be larger. But in the case of MLP, we have a small number of hidden neurons. It will take longer computation time, but here we have a shorter computation time. As the computation time is longer, we have a short learning time, but here we have learning time very long. Okay. So this is the difference between your RBF and LBF. So when we are talking about the curve fitting in RBF, the RBF curve will look like this. We are drawing a circle around the data, but in the case of MLP, we are just separating the data through the straight line, and I'm separating my data. So this is the basic difference between your radial basis function architecture and the multi-layer perceptron architecture. So I hope this is clear to you. What we have discussed today. We discussed about that what is linearly separable data and what is non-linearly separable data. And when you are having non-linear separable data, how RBF will work here and how you are separating the data. You are choosing a centroid here, and you are for expanding and for compressing, you can use any one three function we have discussed. So any one of the function you can use for separating your data. And finally, we have discussed the comparison between RBF and MLP. So this is all about today's class. I hope you understood. Thank you.